Hi, this is Tom Kaler, and I'm going to give an overview that's related to the prior video I did on foundations for generative collective intelligence. In this particular video, I'm going to go into a little bit more depth, and associated with it is a paper that has a lot of the math underpinning what I believe is the next generation for AI systems. And it's all based on information physics. And if I had my preference, I would omit the use of the word AI simply because it is means many things to different people. What it is not, and this is something to understand as you go into this discussion, what it is not is simply learning from data that's historical and extracting knowledge from data. This is complementary to that. What we're going to talk about today is the idea of AI as an amplifier in a learning process, a dynamic, it aids, it wraps around us a exoskeleton that will allow us to learn and converge faster on ideas that are potentially breakthrough ideas. Another fundamental assumption here is that there's a radical difference between how humans think and how our current understanding of AI works. Our current understanding of AI is that if you just train a mathematical model on data over and over again, that's going to give you a product that has intelligence in it. What we're now going to talk about today uh, is how we can get in the middle, use the process of as an AI or as a system is learning the emergent intelligence, that can be an amplifier to people and AI working together to come up with the brilliant new idea. So this is a whole new way of thinking about this as a dynamic learning aid, a way to assist us in thinking together with each other and with AI agents to create the best possible outcomes or the best possible solutions. So the potential product of this is serendipitous discovery, something that's never going to happen by looking at past data. But in the middle of the learning environment, we're going to see that this has the ability to guide a group to discoveries that they would not make uh, in isolation. So the underlying idea then here is that intelligence, as we think about it in conscious beings like humans, emerges from a navigation of hypothesis testing through a series of circumstances and events, sensory inputs. So when we are learning, we are kind of making continuous decisions about what is the best way, what's the best next choice, what's the best next path. That we're going to call that is Bayesian navigation. And what we mean by that is simply we have a belief, we see evidence, sensory input, and then we make a decision based on that in terms of the next step. And so that is the framework we're going to use. And this is really an information physics framework. Uh, this is also very related to work that's being done in the free energy principle and active inference, but it goes a little bit beyond that, and you'll see why. So now let's look at the first foundation. And this is critical. This one you've actually experienced, except we're going to put it on its side a little bit. If you have looked at how PageRank works in terms of ranking information on the web, this is how we brought order to the web. That was the original paper by Larry Page and Sergey Brin uh, and Terry Winograd. The three of them wrote that paper together, How to Bring Order to the Web. Well, what it was an application of these two ideas to the connectivity of links into the web, into various nodes on the web. We're now going to be thinking about replace the idea of a node on the web with a person being the person who is emitting ideas and and possible solutions to a problem. It also could be an AI agent that's playing that same role. Now, what we're going to apply that same thing to is the process of, oh, we can now bring order to our collective thinking together. What this says is that at any one point in time, we can develop a probability distribution of what's relevant to the group. And this is how, if you think about when you're in a brainstorming session, a good facilitator is going to be able to do that, kind of know the state of the group as they go through a discussion and try to use that knowledge of the state of the group's collective mind to guide that process. Here we're talking about the ability to create sort of an information physics model of that, an intelligence model of that to then provide a guidance to the learning process. Now, next, we want to say we need to be able to manage that state. In other words, understand how that all that goes together. And uh, the construct we will borrow from this is what has been used in quantum field theory and in physics, which is the Hilbert space. This is a way to manage a state space for any physical system. Um, and it also applies in information physics to any system. So a Hilbert space is a infinite space. Now, when we work with transformer models, they're finite. So basically, what we're saying here is this is a conjecture right now. It's not a, there is a possible theorem in the paper that if it gets proven, that can move beyond conjecture. But right now, we're saying that by doing this, by saying mapping our language models into a Hilbert space, we now have an ability to lay this on an information physics foundation. And at the same time, this will provide an ability to use this same kind of modeling in the advent of quantum computing. The other thing that comes out of this when you lay it on a Hilbert space is we actually can now develop a topological model of what we call belief manifolds. That is, there we can think of all of what we think of as intelligence as a infinite set of possible hypotheses or beliefs about the world. This can get mapped into a Hilbert space, which becomes a infinite resource to how we can navigate our collective learning. So now what we have is an ability to learn what's relevant to the group. Every little state, every little change, it's dynamic. Somebody comes up with a new idea, that distribution changes. And secondly, now we have a way of navigating this very highly complex space using about our what our shared knowledge is about any particular activity, et cetera. Now, the third foundational point here is we can develop a calculus of learning dynamics. And what that means is at any point in time, this is an evolutionary dynamic process. So at any state in that process, we can look at the learning integral, which says this is what we've learned so far, right? That's a way, and this actually involves something called the Bellman equation, but it's a way of compressing knowledge that's been gained through long periods of time and experience alongside of something that might be new. So this is a bringing a sense of some of the dynamic programming capabilities into the mix here. So the learning integral tells us what we've learned so far. The belief derivative will tell us, well, how steep a climb the learning curve is, or how hard is it to go the next step? So this provides a balance, a way of navigating, so of learning as a continuous, measurable process of belief navigation. Now, if you think about this in living systems, it makes a heck of a lot of sense that what we want to do is make those choices that lead to a better next step, that lead to a better future. This is literally a framing for that. So for any problem, any dynamics, any learning environment, this is going to surround that and help us in that navigational process. The fourth pillar is that this is not new. Uh, about 7, 8 years ago, I think it's about that now, uh, Lynn, Tegmark, and Rolnick did a paper on why cheap and deep learning works so well. Right around the 8 years ago, 9 years ago period, people began to realize the reason deep learning is working so well, it's simply a copy of of how uh, it works within the physics world of magnetism, where you have emergent ordering. It's simply that application of that principle, emergent ordering. And last year, Hopfield won the Nobel Prize in Physics, and for that. So basically, Hopfield saw this in 1983. He literally took the Ising model of magnetism and mapped it into how the brain might work. And he realized that long-term correlations in spin ordering were the equivalent of memory in the human brain. Now, that's a little bit of a leap, and I'll leave you to read the papers on that. But the fact is this is has been known for some time. It's only recently been brought into this is the underlying physics of how deep learning works. It's simply a copy of how nature works. And if you want to look at it, look at a murmuration of starlings. You'll see the fact that they're able to order and reorder based on dynamic change. Keep that principle in mind. This is what we need when we're in a problem-solving environment, the ability to have a system supporting us that's detecting where our beliefs are aligned and encouraging us or whatever in different directions. So, what the essence of the Lind, Tegmark, and Rolnick paper is that they were able to see that this is why we're able to map this into AI. And I'm only pointing it out here to say this has a solid foundation. This is not, sort of a little bit of a leap. Now, the other part of this that is really exciting is that there's also a paper, which is referenced in my longer paper, that says that transformer models are just particle physics. And that's the entire nature of that paper is to show that large language models and transformer models in particular treat particles as tokens, and then the attention mechanism is the interaction field. It sort of defines all of the terms of interaction that could happen. Like you have 16 heads looking at all the different forms of interaction that could happen in a model. And out the other side, you can now set up a dynamics. Essentially, what the transformer models do is learn the resonance modes of knowledge in all that data. Now, you hold that thought as well. We can take the same transformer modeling technology and learn the resonance modes of our evolving thinking dynamically, how our thoughts, and so it can sit there as an infrastructure to help us along and understand again, think about this as sort of a super AI facilitator, whatever you want to call it, but it basically can help us guide. And the important thing here is this is not a passive learner from the data. It's an active orchestrator of a learning process using its knowledge to be able to enable us to think faster, better together, or think more creatively together. Now, the next pillar then is that we can look at information physics instead of context and uncertainty. Now, let's see what this means. So, one of the biggest issues uh, in the way transformer models are used for large language models is they have an infinite context window. And that means that's why you get hallucinations. And that's why in the prompt engineering process, you're giving it context. But for those of you who've used it a lot, you recognize that, wow, that's kind of a wobbly process. Well, that's because you're kind of guiding the focus of the language model. Now, what uh, a mechanism that we bring into play here is the notion of a Markov blanket. Markov blanket is the information physics equivalent of a boundary condition. It says this is going to define an entity or a space or a component. A human being has around them a Markov blanket. In other words, this is their state space in their reasoning. And by the way, no one else, in fact, the individual themselves probably does not really understand what all's going on inside their Markov blanket. But every individual has a Markov blanket. A problem, like we're trying to figure out what to do about climate change, that has a Markov blanket. So Markov blankets give us a disciplined way to partition the infinite Hilbert space of concepts. It just gives us a way to navigate and say, oh, I'm in this context, or oh, I'm in this context. So it gives you a way to bring a contextual mapping to all of Hilbert space so that you can navigate through that. Now, what the free energy principle then provides for you, and there are a couple of different ways we can think about this, but in essence, all free energy is essentially looking at the uncertainty associated with the next step. So what we want to be able to do anytime we're doing navigation is say, hey, I want to pick the next step that I feel most confident in, or I want to pick the next step with the least uncertainty. So that's all this calculation is. It's just a calculation. The intelligence is in how do we choose those next steps? How do we navigate this belief space of Hilbert space using this principle of I want to navigate based on confidence. By the way, evolutionary wise, it makes a lot of sense. I basically want to make the choices that are going to keep me alive. And that's sort of the fundamental idea as it's interpreted within the free energy principle school, Carl Friston's work. So therefore, now we have a ability to have an information or semantic geometry to these discussions. I hopefully you get a sense of that. So we can now learn resonance modes of relevance, and we can begin to see how we have this infinite dimensional belief space that we can now navigate. Now, in typical language systems today, they're looking at when they're looking at, say, semantic similarity, they're just doing what's something called cosine similarity to see how those vectors overlap in hyperspace. There's a lot of literature and discussion about things like the standard distant metrics begin to get kind of murky when you're dealing with high dimensional spaces. And so what we bring in here now is something that's I think a little bit more discipline in terms of looking at the information or probability distributions over those vectors. So what we're going to be talking about in generative collective intelligence, we're not just using raw vectors that are learned about a concept, but because we know that that particular vector, that concept may be highly relevant to the group, is a higher probability of relevance, we can now navigate belief space based on the relevance of those various beliefs. And we can use the Fisher-Rao metric for that, which creates a way of looking for the natural gradient flows of thinking. So putting that all together, we now have a way of navigating in a context. Now, the other part of this is, and can't go into it in great detail here, but it turns out that this works across any hierarchy. And this is where we bring in the renormalization group. So let's go back to magnetism, my favorite thing. And by the way, I didn't mention at the beginning of this, that's my PhD in applied physics is in magnetism. And so this has been my deep inspiration in AI for my entire career. Now, the renormalization group works this way. If I have two spins that interact or they're attracted to each other, and if I have a nearest neighbor interaction attraction, that scales. Again, go back to the murmuration of starlings. The birds that are flying close to each other stay aligned with each other. And so what we can now look at is how does nearest neighbor behavior scale to macroscopic behavior. That's called the renormalization group. Um, and that is a very powerful concept that can be used in this context. It was also used in the Lynn Tegmark Rolnick paper. So this gives us a way now. We've got natural gradient flows. We have a way of managing hierarchy. We have a way of managing context. So now what we can look at is we bring that all together. We now, if you start to put all these pieces together, we can actually say that for any group, uh, thinking about any problem or learning any topic, we can bring that group to a place of conclusive convergence. There is a state of convergence to a conclusion that will represent the state of least uncertainty for that group or the state of highest confidence for that group. So we have an ability now to looking at what does the group feel most confident about a decision or a policy or whatever it happens to be. This actually could be applied to scientific thinkers, scientific literature. What is the greatest confidence we have in a theory? This whole system is designed on the method for scientific knowledge discovery. So it doesn't surprise that it applies there. So by relaxing deterministic constraints, now we can take out a theorem that has maybe plagued us for a long time, which is Arrow's impossibility theorem. Basically, Arrow's impossibility theorem says you can't please all the people all the time. It actually says that there is no voting system that's going to result in complete alignment in a group. Now, that's a deterministic thing. What we're saying is if you now relax that there is absolute agreement, there is some state that's a relative equilibrium for that group. Now, what this opens us up to is we actually have a mathematical way to deal with compromise and deliberation. We can actually say, oh, well, this is the best. And by the way, there can be some groups where the free energy will increase as they interact as opposed to decrease. We're just saying this is a framework for evaluation, not that it's going to always be copacetic where that minimum point is. It could end up, I mean, again, we're talking information physics. So like in any physical system, you have all the possibilities that might happen. Now, finally, we can bring this all together in the fundamental theorem of adaptive collective learning. Um, we can maintain identity uh, within various problem spaces or contexts or whatever using the Markov blanket. So we can basically begin to do universal context management. Second, we have optimal information processing capabilities with this because we can now have a flow of the natural gradient of information within the belief manifold. And we also have an ability to look at hierarchical emergence using the renormalization group. So we wrap this all under something we call collective reasoning, which is a reasoning process for adaptive collective learning that leads to causal models of the collective mind. Now, the other part, the problem with we didn't talk about at the very beginning of this, and this is actually, it could be there, but uh, there is another issue we have to deal with. When you have in the real world a group of people together, it breaks down very quickly. And we know this is the Brooks law, the law of communication complexity, which says that uh, if you have seven people in a group, you just look at it, there's 21 lines of possible communication. This means if we have to define now what do we need to have a level of deep listening. I mean, what we've come to is just say, hey, look, it's just going to have to be a few people make the decisions. This is often what happens. I have a friend who is a CEO. I said, look, I try to listen to everybody, but at the end of the day, I can't get everybody to agree. So I just have to make a judgment call. That's high risk. And that's how people get become heroes. It's how people lose their jobs. Um, there is a new way, which means that we can instead of having the sequential interaction of you speak, you speak, you speak, you speak, we can now go to a parallel model. And that's what this whole architecture that you saw so far, it opens up the possibility that whether it's 10 people, which would have about 50 lines of communication, or 100 people, which has about 5,000 lines of communication, it all works the same. We have infinite scalability. And this is a big deal because we can now potentially listen to everyone about a policy, a democratic policy, or a health policy. We can listen to a community. But also, if you're in a corporation and you really know that you have about 25, 30 people that are relevant sources of knowledge for this particular important decision. And by the way, that number is probably small in most cases if you include marketing, sales, engineering, finance, partners, customers, et cetera. Whenever you're making decisions, it's highly entangled. So the size of the group matters. And so it's very important that you are able to do this. Now, the way we break this communication barrier is we use something we call a sampling function. The core learning function here is, and I call it the beta sampler, because quite often when the old method is alpha, somebody decides, power move. We're in a global struggle for that right now. Can we solve our problems? We just have to bring in a strong man. I mean, this is the essential issue, and it's largely because you can't get convergence as soon as you go to a larger group. So here's the answer to that. I really believe this is the answer: is that you can design a sampling algorithm that balances between convergence and divergence. And you can have an attention parameter that looks at remember, we know how it can manage context. So the beta sampler can say, oh, for that question, there's probably about 300 things unique concepts about that. So let's just explore those. You see how that immediately allows for focus. And now what it's doing, it says, well, let me just sample broadly and start to learn what the group might consider important. And then as they learn what they consider important, it begins to use that probability distribution of importance to decide what to say next. So it can move the group, just like a good facilitator does, by putting yellow stickies everywhere to ending up with a list of priorities. That can be done at scale to a group of any size, with a group of any size. So that's really basically it. You can have scale-free collaboration. Now, this has been built. We started building this well over 10 years ago. Uh, Now it's being emerging in a new architecture, which we're calling the agent interface environment architecture. Uh, but it is available in the more classic form, or there's some new forms that we're developing. Ultimately, we're going to move this into an API, and I mean not long term. I mean it hasn't been released yet, but there are multiple APIs that we have currently that can open up this technology to be incorporated in a wide variety of applications. And for those of you who follow CrowdSmart, this is the new CrowdSmart 2.0, is to begin this thing, realize this technology is infrastructure technology. Therefore, we want to make it available to be integrated in with anything from Miro or whatever applications out there. We want to be able to bring this notion of collaborative learning into a wide variety of tools and capabilities. So, conclusion, we have a paradigm shift and we have a way to do it. um, we can shift from a sense of learning from our data droppings, which none of us would agree is our best, to generative collective intelligence, where we can actively create dynamic learning environments, where we can actually not remove what was come out of generative AI, but bring it into an environment where you actually can sift and winnow that which is of value and importance. So we can think of this as almost collaborative prompt engineering, of each other and AI agents. I mean, we're basically able to now shift from what we did before to intelligence application, amplification, and value creation, as opposed to looking at AI just as a way to reduce cost, automate tasks. We now can look at it as a way we do value creation. So with that, uh, I want to thank you for listening, and you can reach me at tom@crowdsmart.ai. The paper is also available on my ResearchGate, uh, and I think it's publicly available there. So you can just look me up on ResearchGate or send me an email. Thank you very much.